Hello, this is lecture 11. We are still doing velocity analysis and using equations. And okay, I have this example for you. Okay, I have two loops here. This is link number. I have how many links I have in here? I have two, three being the slider. That's three, this slider. Four is actually this link here, the rocker, and then this is five. And 6 is other slider at point C. That's the sixth link. All right, so I have then this will be my omega 2 from x axis positive, theta 4 for link 4. These are all variables. Um, this distance here will be a variable distance. That's r3. I note that as well, and I needed to find the velocity of this point. And then this here will be R4 and this will be R5, and so this will be theta 5 over here type thing. Okay, so this distance here, we can refer to this distance as xc or something, this distance here. That's slides. That slider C slides on this line here. Okay, now I have two loops. When we look at this, this is one loop over here, right? And we may have done something like that before. And this is my second loop. So that's loop one and loop two. Second loop, I'm going to take the big, like sort of, this distance here, h and j, like pi over 2, this vector, and this vector here, right? And this will be xc, this vector will be xc ej0, this vector here, and then I'll be able to close with those two vectors, r4 and r5. So this will give me a large loop. Now, and the small loop has r2 and maybe r1, if we want, that's r1, and this will be r3. So r1 is aj 3 pi over 2, and r2 and the distance, of course, r1, so that's constant distance r1. R2 is r2, aj theta 2, r3 is variable length r3, aj theta 4, and then I have r4, which is this here. This is constant length r4, aj theta 4, and then I have r5, which is r5 constant length aj theta 5, and maybe I can say r6, which is h at 90 degrees plus xc at 0 degrees. Together they give me rx. So I have the first loop will encompass those three vectors. This will be loop 1, and this will be loop 2. Loop 2 will be those other vectors. And now when I look at these loops, every loop is really by itself a single degree of freedom linkage, and tells me it's possible to do like it's just one loop closure equation per loop, can find everything we want per this loop. So we can do the first loop, and then we can calculate theta 4 from this loop and omega 4, and then we move on to the second loop, which is also second degree, a single degree of freedom, and then we can use this theta 4 and omega 4 as the input to the large loop as well separately. So we can, the problem like this can be divided into two smaller problems, and we can be connected together to link the answer from one to the other. So let's do that. Let's go r this here. I have the equation for my first r1, or yeah, that's r1 plus r3 is r3 going to point A. R1 is from O1 to O4, two fixed points, plus R3. This will give me R2, which will close this loop for me. and then I write those in the polar form. So that's R1 constant, a to j 3 pi over 2 constant angle, plus R2, which is variable length, times e to j theta 4, which is variable angle. So, and then I have R2 e to j theta 2, and then when I differentiate that to find my velocity equation, I'll get 0 here, plus when I differentiate this, don't forget this will give us two values. You differentiate R3 will give me the sliding velocity along 4 and in the direction of 4, and then we'll fix R3 will give me omega 3 R4, a component perpendicular to link number 4 as we did previously, and then over here I'll have R2 omega 2 AJ theta 2 plus pi over 2 type thing, and then I can then do I and J, and then I have real over here, and the real will be uh, the real is like, that's why what I mean by I and J. Really, I mean for I mean the real, and then will be Vs cosine theta 4 minus R3 omega 4 sine theta 4 being equal to minus R2 omega 2 sine theta 2, and then the other scalar equation, which is an imaginary one, would be Vs sine theta 4 plus R3 omega 4 cosine theta 4 being equal to R2 omega 2 cosine theta 2. And if I arrange those together in a matrix form, I can have Vs, I can have R3 omega 4 type thing, and here inside that I can have my Jacobian. On the other side, I'll have R2 omega 2 minus sine theta 2 cosine theta 2. Here I will have cosine theta 4 minus sine theta 4 sine theta 4, and here I have cosine theta 4. Now this is the Jacobian of theta 2 here. That's with j theta 2, which is cosine theta 4 minus sine theta 4 sine theta 4 cosine theta 4. The determinant here of that simply equal to 1. That's 1 because you multiply cosine squared plus sine squared, which is 1. This is a determinant, and then j theta, or then I replace this column, second column, by the right hand side. Then I'll have cosine theta 4 sine theta 4 minus sine theta 2 cosine theta 2, right? This is my Jacobian, which is the j theta 4. No, that's not a determinant. This is the matrix itself. So I should remove those signs. And over here, the Jacobian, the determinant of this Jacobian is equal to, you multiply cosine, you get cosine times cosine, minus sine times sine will be added. So this will be cosine the difference, theta 4 minus theta 2 type thing. So that's then cosine when you multiply those together, because you get two cosines and plus two sines, which is cosine the difference. And then I have the Jacobian, which corresponds to R3. So I replace the first column by sine theta 2 cosine theta 2. Second column remains as minus sine theta 4 cosine theta 4, and this is Jacobian, and then the determinant of that, I get it when I multiply across like that. So I multiply those together, will give me minus sine theta 2 cosine, and then this will give me plus those added together. So this will be equal to sine theta 4 minus theta 2, right? Because I mean this will be like the outcome of that is really sine theta. I can write it here for you, so I don't want to be confused. So this because this was equal to sine here. Let's use that specific color here. Okay, that's a better color. All right. So if we say this will be sine. Okay, so this will be sine theta 4 cosine theta 2, take away sine cosine theta 4 sine theta 2. So this gives you sine the difference type thing. All right, so now sine the difference. Now, so I have my three coefficients, velocity coefficients, or three Jacobians, if you like, the three determinants. So I can write the equation which says omega 2 R2 over its associated determinant. This is equal to omega 4 R3. This should be R3, omega 4 R3. Divide this by associated determinant, which is J theta 4. And this is equal to V sliding. Divide this by associated Jacobian, which is JR3, right? Type thing. And then this will be omega 2 R2 is equal to omega 4 R3 over J theta 4, which is cosine the difference. So this will give me cosine theta 4 minus theta 2. And here I'll have V sliding, and underneath I'll have sine theta 4 minus theta 2. And I can get from here, I can get expression for omega 4 and the sliding velocity. That's easy to get by equating both each term to omega 2 R2, and I get the information I'm after. And this tells me exactly what will happen when Vs is going to be equal to 0, when this sign is equal to 0, meaning that when the sign is equal to 0, this means the difference between the two values here are either 0 or pi or multiple of that, and this will happen. The two values with theta 4 and theta 2 I meant will be, if the difference is 0 or pi or multiple, then this means this determinant under Vs is going to be 0 and the sliding velocity will cease. And at this point in time, the slider A would have gone to the extreme positions on link number 4 up and down, and one of them when link 4 and link 2 are on top of each other type thing. Both in fact will be on top of each other, but the angle once will be 0, and then the angle will be 180 at another position. And the same if I look at omega 4 and how when omega 4 is going to be 0, the omega 4 is going to be 0 when this Jacobian underneath omega 4 is going to be 0, and then or this determined, and when cosine the difference is 0 means the difference is 90 or multiple of 90, and this will take place when the crank is perpendicular to link number 4, as we had discussed previously. So when we did the extreme position thing at the start of this course, like when the angle here is 90 degrees, then this means this would have gone to the extreme position, right? Type thing. Right, we have done this previously. All right, so you get all this mobility information from my velocity analysis when I use my Jacobians. Right, now if I move to the next part or the next loop, I'll have, then I can just add those, like I can add this here, this vector, which is, like I can say R6, which is the sum, this sum together, right? R6 is equal to R4 here plus R5 here. So let's write this expression, and okay, let's see what will happen. So I'll go R6 is equal to R4 plus R5, and R6 was actually two parts, like the vertical a to j pi over 2 plus the horizontal xc a to j 0, that's equal to R4, which is constant length R4 aj theta 4 plus R5 a to j theta 5. So that's theta 4 and theta 5. Now, when I differentiate that, I get the velocity expression. This will be 0, so this will be 0 plus vc e to j 0 being equal to R4 omega 4 e to j theta 4 plus pi over 2 plus R5 omega 5, right? Omega 5 e to j theta 5 plus pi over 2. And then when I do real equal real and imaginary equal imaginary, I will get the information I'm after. So this here will give me VC cosine 0, which is 1. That's equal to minus R4 omega 4 sine theta 4 minus R5 omega 5 sine theta 5. And the imaginary will give me the other expression. So this real and this imaginary will give me the other expression, which is 0 is equal to R4 omega 4 cosine theta 4 plus R5 omega 5 cosine theta 5. When I arrange my equation, I can then move theta 5, R5, this like omega 5, this other side because it's not known. So I can say then VC plus R5 omega 5 sine theta 5 being equal to minus R4 omega 4 sine theta 4, and here I have R5 negative omega 5 cosine theta 5, that's equal to R4 omega 4 cosine theta 4, and I can write here my equation by saying VC and R5 omega 5, that's linear system of equations, will be equal to 1. Here I have sine theta 5. This is equal to the other side. If I take R4 omega 4 is common, then I have minus sine theta 4. The other equation, I have cosine theta 4. Here I have 0 because there's no, this is 0 times VC, so VC is 0. And here I have minus cosine theta 5, right? So this was just nothing here. This was supposed to be omega 5. All right, okay. So now this gives me the Jacobian, which is j theta 4, right? Okay, we had in the previous loop, we had another j theta 4. Remember this one? Okay, so that's not the same. I'm going to refer to this as j2 theta 4, just to differentiate it. So j2, the second Jacobian for theta 4, is equal to 1 sine theta 5, 0 minus cosine theta 5, and the determinant of that when I need it, j2 theta 4, this determinant, that's equal to minus cosine theta 5. Okay, that's minus cosine theta 5. And then what happens here is I can find the other Jacobians. So I have j theta 5, for example. So I can swap the second column by the column on the right hand side. So I have 1 minus sine theta 4, 0 minus cosine theta 4. No, that's plus cosine theta 4. Okay, so that's plus here. Okay, so I just swapped this column by the column on the right hand side, and this will give me cosine. So the determinant, this determinant here, will give me cosine theta 4. All right, okay. So now, what if I want to find I have a third, which is a third Jacobian, JXC. I replace the first column by the column on the right hand side. So I have minus sine theta 4, and I have here cosine theta 4, and here I have sine theta 5 minus cosine theta 5. And then when I solve that to get, let's get my sort of determinant, I'll just multiply those together. Will give me sine cosine minus cosine sine. So this will be sine the difference between theta 4 and theta 5. So this is sine theta 4 minus theta 5. Now I have those Jacobians. I can rearrange my equations together to get the values for these velocities. So to find these velocities, just as simple as using the ratios we discussed before. Like if I wanted, now I can go, if I use the ratios, but before using the ratios to get the velocities, let's do some mobility inspection first and see what happens where the like end points or stationary points are going to appear in this linkage in the second loop. So, okay, so now regarding this specific um, determinant here, j theta 5, which tells me well, link number 5 is going to be stationary. Link number 5, if you remember, was actually this link here, which links the rocker to the slider. And this, you expect this to be stationary when this point B has reached its highest possible point, like it's when, oh, okay. And this says, this what actually tells me here. It says, this expression tells me that by saying this Jacobian, the determinant of that is going to be equal to cosine theta 4. So when theta 4 is 0, when theta 4 is 90, cosine 90 is 0. So this determinant is going to be 0, and this will be an extreme position of the link number 5 type thing when point B has reached the top value, and obviously it will. This is just imposed by the geometry of the system. There will be a situation when if link number 4 stops, also those other links for 5 and 6 will stop with it as well because they are in the equation, and as we'll see in a second. But this is just here, that's an interesting situation as to when link 5 is going to stop by virtue of the geometric constraints we have in the system. And this other one here, this other Jacobian, the sign difference between theta 4 and theta 5 tells me when the angle between them is 0 or whatever, then if theta 5, if link 5 is stretched along the link 4, then expect the slider to stop at this point in time by virtue of geometry. But I think the linkage will not allow this to happen, just will stop when theta 4 stops, when theta 4 is equal to 0, when link 4 is perpendicular to link number 2, as per this discussion earlier. So when link 4 is perpendicular to link number 2, link 4 is going to stop, this link here is going to stop, and then we'll stop the rest of the loop 2 with it type thing, right? So we have geometric constraints that may not be reached during the rotation. I'm not sure if it's possible that theta 5 and theta 4 will be aligned, will have the same value or whatever, or link 4 and link 5 will be aligned during the rotation of this linkage, whether the crank will allow this to be the case as it rotates. Okay, in any case, we get geometric insight into the working of the thing using those Jacobians, and the determinant of the Jacobians are of paramount importance because of that. Now, if I wanted to have my equations, I'll go omega 4 R4 over the Jacobian, which is associated with that. It was J2, wasn't it? J2 theta 4. I'm going to just note that here. So this is J2 theta 4 is determined. This will be equal to R5 omega 5 over the Jacobian, which is associated with theta 5. And then That's also VC over the Jacobian, which is associated with XC. So that's JXC, and that's the determinant of this specific Jacobian. So now I can equate those, like I can equate every pair, like each of theta omega 5 and VC separately, those terms with the omega 4 term, to get an expression for those velocities. And it is obvious from those expressions that when omega 4 is equal to 0, the other velocities will be equal to 0 as well, because link 4 is the feed into, or the input link to the second loop. Now, it's if you wanted to replace, like use the fact that we had another expression for omega 4, remember from the previous loop, omega 2 R2 over j theta 2 in loop 1 was omega equal to omega 4 R3 over j theta 4, the determinant. Then we can make a swap here and replace omega 4 by this expression. So we can say omega 4 is equal to, from here, is equal to R2 over R3. I have here omega 2. Underneath, I have J2 determinant, and I have the determinant of J theta 4 at the top. And this will give me this expression for omega 4. I can now use it over here to find expressions for omega 5 and VC in terms of omega 2 if I want to. That's quite possible to achieve. So I can say, here I can say R5 omega 5 of J theta 5 is equal to VC over JXC. That's omega R5 omega 5 on J theta 5. That's equal to, replace omega 4 here by omega 2. So you end up with R4, right, times R2 over R3 and omega 2 over here, and then some Jacobians related together. So you have, here you have J theta 4 over J2 theta 4 multiplied by J theta 2, those determinants together. And then you can straight away link omega 2 to, which is the velocity of the crank, to the velocities of all links you have in the linkage. And this was quite possible because I have to, it's quite possible, it was a fairly simple example because I had two loops and every loop was not connected to, had only a single degree of freedom, so it can be solved on its own. Right. This is not always the case. Sometimes you get complicated cases, like for example, I'll just possibly try to find an example here which shows an interesting situation. Well, okay, well, we have this example which I did speak about before. So let's say this example here. Okay, so if we have here, if I take this example, and I wanted to do a position or velocity analysis for this example here. So let's say I just flatten this to stay with my page. All right, so this here I have also two loops. So let's see what we can do with something like that. This is my link number 2. This is 2. Then I can have R2 over here, and then this can be R3, and this can be R4, and this here is a slider type thing. So I have, which is the fifth link. So this one loop, this is loop 1, has 5 links. So by this loop 1 by itself has 2 degrees of freedom by itself, right? So it's not possible, like it will be quite like if you cannot solve it unless you have actually two pieces of information, two velocities or whatever, right? However, the linkage as a whole has a single degree of freedom. The reason is it's actually linked, everything is constrained by the motion of the second loop as well. So the two loops together, each one has 2 degrees of freedom. If you look at it separately, but together they have a single degree of freedom. So as a whole linkage. So in this case, the situation is different from before, and we may not be able to have two different smaller problems, if you like, link, and then we can link them together. So let's say if I wanted to do that, this is here would be theta 2. Let's say this angle here is constant. So we'll call this angle phi 2 or something. Okay. Or just, yeah, we can just call it phi 2 and we know it's constant angle. And then this is another linkage, another vector related to link number 2. So I can call this R2, 2, like 2, the second one, 2, right? I can say this is R4. I can say this is R4, 2, the second one or something like that for R4. This here, I can say this is R5. And now my links, so over here, I will have also distance. So this point here, I'm going to call this point, let's say, okay, I'll just give it a name. We can call it point C or something. Just that's point C. Then this distance is XC. So, and this will give me vector R1. So this vector R1, if you want to find, let's find expressions for these vectors. We can find this expression. So we can go R1 is XC e to J 0, and then I have R2 is well, we need to give them some length. So I'm going to call this R2 small. Okay, there's different color. So I'm going to call this small. That's R2. So R2 AJ theta 2, and then R3 small R3 AJ theta 3. That's variable. This will be R3, and R4 will be R4 AJ theta 4, and then I have R other vectors I need. So this will give me very much my first loop. So my first loop will be R1, right, is equal to is equal to is equal to R2 plus R3 plus R4, right? So how many angles we have here? How many degrees of freedom we have here? So R1 has XC, that's a degree of freedom. This is one piece of information. This is R2 has theta 2, you can say that's given, and R3 has theta 3, that's an unknown, and also here theta 4 unknown. So have how many unknowns we have? We have 3 unknowns. Those are my unknowns here, right? And the loop equation will give me only two scalar equations, so will not be sufficient to do 3 unknowns. Hence, I need to use the second loop as well. All right, so let's look at the second loop. Second loop will have R22, in the second loop R22. So we can say R22 is equal little R22 constant AJ, right? Theta 2 plus phi 2, because that's a constant angle that doesn't change. And then I have R5, which is R5 AJ theta 5. And I have R42, which is equal to some distance here. This is R42. And then there will be the difference between those two. There will be a specific angle which we can use to relate those two together. And this angle we can refer to it as phi 4 or something like that, and this will be constant, and you can get it simply by looking at the the definitions, the angles of the triangles, and find that. So it's all right. Going to call this R42 AJ theta 4 plus phi 4, which is constant, right? So and then well, in this case, I can write the equation for the second loop. So the second loop, the equation will look like what? Will look like R1 is equal to R22 here plus R5 plus R42. So the second loop will be R1 is equal to R22 plus R5 plus R42, and then R1 is still okay, here is I have XC, that's still unknown, and R22 is known because it has theta 2, I know that, and there is phi 2, but it's constant. R5 has theta 5, that's not given, that's an unknown, and this has theta 4 unknown as well, but phi 4 is known. So how many unknowns altogether here? I have also, I have 1, 2, 3. I have the same unknowns like the loop 1. So this is loop 1. This one is loop 2. So between the two loops, how many unknowns I have got? I have x, this is loop 2. My unknowns are, I have xc, theta 3, theta 4, and theta 5. Theta 4, theta 3 of this link has theta 3, and this one has theta 5, and this one has theta 4, and this one has x as an unknown. 4 unknowns. Okay, now I have 4 unknowns, and I have 4 scalar equations, because each loop closure will give me two scalar equations. So let's do them and spread them and see what sort of equations we get. So okay, so the first one here, R1 is, I'll just write x1, right? EJ0, that's equal to R2 EJ theta 2 plus R3 EJ theta 3 plus R4 EJ theta 4. This is my first equation, right? And then I used those vectors. And then my second equation, I use those 3 vectors plus R1 again. So my second equation has in it R1, which is x1 EJ0. That's equal to R22 EJ theta 2 plus phi 2, which is constant, plus R3. No, this in fact should be R5. So I'm using here. So this should be R5 EJ theta 5 plus R4 2 EJ theta 4 plus phi 4. This here goes into that. All right. So I have my 2 loop closure equations, and as you can tell, I have more unknowns in each equation than 2. Then I need to solve, but luckily we have 4 in total. Then the 4 equations should be sufficient. Now I would imagine if you try to solve this to find the angles, or like theta 3 and theta 4 and x as function of, and theta 5 as function of theta 2, it will be quite difficult to solve those equations together in terms of position analysis, right? But velocity analysis is really straightforward. So let's imagine that I have my positions and I'm doing my velocity analysis. So the first equation, when you differentiate that, you'll get VC EJ0, and then that's equal R2 omega 2 AJ theta 2 plus pi over 2 plus R3 omega 3 AJ theta 3 plus pi over 2 plus R4 omega 4 EJ theta 4 plus pi over 2, right? And then I can, out of this, get 2 scalar equations in a second. And let's do the other equation as well. And okay, the other equation, I'll have VC EJ0. That's equal to R22 omega 2 AJ theta 2 plus phi 2 plus pi over 2, and then plus R5 omega 5 AJ theta 5 plus pi over 2 plus R42 EJ theta 4 plus pi 4 plus pi over 2. This is my second loop equation, sort of differentiated. Now, if I want to do my reals and my imaginaries, so I go real, first one, I get R2 omega 2 minus, no, I can actually have on the right, on my left hand side first, I'm going to have VC will multiply by cosine, and that's cosine 0 is 1. It's equal to minus R2 omega 2 sine theta 2 minus R3 omega 3 sine theta 3 minus R4 omega 4 sine theta 4, and then the imaginary is going to be 0 being equal to R2 omega 2 cosine theta 2 plus R3 omega 3 cosine theta 3 plus R5 omega 5 cosine theta, no, R4 omega 4 cosine theta 4. And then my second equation, when I do the real for the second equation, it will be VC being equal to R22 omega 2, correct? And then there is negative here, negative sine theta 2 plus phi 2, negative again R5 omega 5 sine theta 5, and negative again R42, then omega 4, and then inside here I have sine theta 4 plus phi 4, which is constant, and then the imaginary part of my second equation will give me 0. Here I have R22 omega 2 cosine theta 2 plus phi 2, then plus R5 omega 5 cosine theta 5 plus R42 omega 4 cosine theta 4 plus phi 4. Now I have those 4 equations, which now I am forced to solve together. I cannot do every two separately because I have the unknowns in this equation are quite considerable, and if I take, like, it would be really complicated if I try to take VC from one expression and chuck it in the other expressions. Maybe VC will disappear, but I have lots of sines and cosines in my expression. So you can do whatever mathematically, like whichever method you are familiar with to simplify the equation. That's not a problem at all. Like, it's I mean, yeah, it's quite possible to do whatever, but then one possibility is if we decide to, we find it will be complicated if we try to break it down, and then we can just do it together in the one whole go. So we'll write one big Jacobian, if you like, to sort of represent the differential relationships in this system. So I'm going to do them together. So I'm going to have over here, see if my space here will allow me to do more on this page. So if I have my first equation, so I decided to have in the first row VC, for example. So I'll have over here 1, right? And then I will have over here minus, I'll have plus R3 sine theta 3, and then I will have over here R4 sine theta 4. So now my Jacobian has radii inside it, just because I realized I'm doing all the four equations together. And over here, like for example, I have omega 2 R2, but in the second equations, I have omega 2 R22, different length. All right. So, I mean, if the length was the same, I would have I just used omega 2 R2 as an unknown outside. But because it's not the same, R is not the same thing applies, same problem I faced and with R2, R4 omega 4, but in the other set of equations, it's R42 omega 4. So because of those two cases, I just decided to have omega as my variable outside and have R inside the Jacobian, which is exactly the same thing. That's no problem with that at all. Mathematically, that's absolutely fine. And then okay, so but this column here would be the VC column. This one will be the omega 3 column. This one will be omega 4 column. I have another one which is omega 5 column. All right, so omega 5 in the first equation, I don't have omega 5, so this will be 0 over here. All right, so okay, the other side here, I will have minus R2 sine theta 2, right? So over here, I'm going to have omega 2 as like a common matrix here, a common variable or uh, common factor. The right. So here I'm going to have VC, then I'm going to have omega 3, then omega 4, then omega 5. So I'll have this will be my set of equations. Okay, let's hope I have enough space to do it. All right, so VC, my second equation, equation 2, VC doesn't appear, it's actually multiplied by 0. Omega 3 in the second equation is multiplied by minus R3 cosine theta 3, and then omega 4 is multiplied by negative R4 cosine theta 4, and no omega 5 as well, so that's 0. On the other side, I have minus R2, so decided to move those to the other side. So this will be, that's equation 2. So this will be R2. Here I'll have R2 cosine theta 2 plus. Okay, and then the third equation. All right, so VC is multiplied by 1, and I grab omega 4 to the other side and omega 3 and whatever. So omega 3, it doesn't appear, so omega 3 would be 0. Omega 4 will have R42, right, sine theta 4 plus phi 4. And then this will be this term. And on the other side, I will have negative, and then omega 5 also will move to the other side, will be plus R5 sine theta 5. And then on the other side, I have minus R22 sine theta 2 plus phi 2. This is on the other side of the equation, right? Okay, I don't know if I can clean this a bit. Oh, okay, now that's difficult. Right, so I'll just possibly just leave it and pretend we can read this is sine theta 2 plus phi 2, and then the last equation, VC corresponds to 0, and then omega 3 does not exist here, and then omega 4 corresponds to this specific term, so that's minus R42 cosine theta 4 plus phi 4, and then I have omega 5, which has here minus R5 cosine theta 5. Here I have plus R22 cosine theta 2 plus phi 2. All right. So this is my linear set of equations. That's my linear equations. And this is my Jacobian here, which is j theta 2, which is this is equal to 0 for any reason during the rotations. Then the crank is going to stall and the whole linkage will stall with it if the crank is meant to do 360 rotations. And then same thing if I wanted to have VC, so I have different Jacobians. I'm not going to calculate this Jacobian. I would really, a Jacobian such as this one, a problem like this one, I would really do on a computer instead of doing manually. I'll just try to find expressions for my Jacobian like I've just done this with this sort of expressions, and then I take those expressions for computer to do further calculations of determinant and stuff like that. But I can say that my JXC is equal to, and just copy this Jacobian here and replace the first column, which corresponds to XC or VC, by the column on the right hand side, this column here, and call this Jacobian GXC, right? Sort of thing. And then I have also J theta 3, I have J theta 4, I have J theta 5 as well. So, and then I have all those Jacobians. I can write my equation. In this case, my ratio, the ratio thing that we did previously, I can write it, but different form this time around. I can say it's omega 2 without r this time around, right? Omega 2 over J theta 2 is equal to VC over J XC, right? And then that's equal to omega 3 over J theta 3, that's equal to omega 4 over J theta 4. And then this way I get my expressions. But as I said, I would do this on the computer. So I would input on the computer and I program this, and I input the expression, if you like, on MATLAB or whatever, you input a matrix, you call it J theta 2, JXC or whatever, and then you input the expressions into for the different entries in the matrix if you like. So that's more of a programming thing. Okay, so now a problem such as this one, it's quite difficult to do a position analysis for. So like it's if I want to do position analysis for a problem like this one, I'll just, and now I have my loop closure equations which I differentiated those loop closure equations, like four equations, two equations, four scalar equations, and then try to solve together. And I have lots of sines and cosines and sine theta plus phi and this sort of stuff. And so mathematically it will be quite complicated to obtain closed form solutions for the angles and xc as function of theta 2. And in this case, if we want to do position analysis, we do it in an inverse fashion. So we do our velocity analysis like we did here, and then we integrate numerically, like so numerical integration, right? We integrate the position, the velocity expressions to get the positions of different links. And with the positions of different links, you have done your position analysis. But when we do it, this will be a topic called the computational kinematics, which I'm going to explain in my soon. Like maybe that's my next topic, as it's still part of velocity analysis, right? Sort of thing. But just give you some idea. Now, if I have that's VC, if I have an expression for VC, this is JXC over J theta 2. I forgot to put the determinant sign here, right? And then determinant sign times omega 2. And then I have omega 3. This should be, I have also another omega, right? I have omega 5. I have omega 5 over J theta 5, right? So omega 3, which is equal to then J theta 3, this determinant, over j theta 2, this other determinant, times omega 2, and then I have omega 4 being equal to j theta 4 over j theta 2 determinant times omega 2, and then I have omega 5 that's equal to j theta 5 determinant over j theta 2, right, times omega 2. Now I have those expressions. So if I have theta, if I can integrate now, the problem is becomes if I want to find xc, integrate, right, v c, right, dt type thing, and then it becomes an integration problem. But so work backwards. But I'll explain how to do this integration, because it's not done with, like, it's not closed form integration. It's more of a computational, computer-based type analysis type thing. So we start from a given set, like given configuration for the linkage, where all angles are known, theta 2, theta 3, theta 4, theta 5, everything, xc, everything is known, like would be like starting at an assembly position given to you in AutoCAD or drawn somehow to scale, and then you can measure those angles from the given drawing, the drawing given to you, and then you start integrating a step by step, incrementing the crank angle. You start from the given crank angle, then you increment it a little bit, like, let's say a degree or half a degree or something, and then you calculate the corresponding motion in other links, and keep incrementing and so on. This topic is called the computational kinematics, and without this, I wouldn't be able to find the closed form solution for a problem like this. So the topic is quite important, especially when you're handling complex complex linkages such as this one, and you are trying to find a position analysis. Of course, the position analysis we're going to get by this method would not be a closed form, but more of an array. So we'll get at theta 2, and here theta 3, theta 4, theta 5, xc, and whatever. So we change theta to a number of times. We get the corresponding values of those other theta's other link positions and angles and stuff like that. And then till theta 2 has done all 2 pi, and then we get a table, a big table of all the angles matching together type thing. And then we can plot the relationship between the angles and theta 2 and so on, right? So this topic is called the computational kinematics. It is my next topic. All right, well then, till the next lecture, please have a look at those examples. Try to do things by, like, try to obtain those models by yourself. And if you get stuck, drop us a line on Moodle or by email. Okay, thank you.